This video is going to give an overview of generalized estimating equations, more from like an epidemiologist perspective as opposed to a statistician's perspective. So just kind of describing what it is and how it's used, as opposed to the nitty gritty of the actual like what's going on under the hood. So the main situation you'll see generalized estimating equations used is longitudinal data, so data happening over time, where there's repeated measures. So like taking repeated measurements in an individual, like maybe once a month, we're taking blood tests and measuring just some outcome like cholesterol level multiple times over follow-up. That's a clustering situation basically, where it's repeated measures from the same individual, and those measures from any one individual are likely to be correlated as opposed to two separate individuals. So for that reason, GEE is useful in other clustering scenarios. So a situation like if you have some question that is related to some health outcome in school-age children, you might sample kids from a bunch of schools, but even especially if it's infectious disease, kids from the same school are likely to be correlated in whatever their outcome status is. And if there's any genetic or parental influence thing happening, then children from the same family are likely to be clustered. And GEE is a way of taking care of that, because one of the assumptions of pretty much any other modeling process is independence of the data, and that means that basically one individual's outcome or exposure status isn't related to another's. And this is a situation where they are related. So just kind of going into that a little bit more, here's like a motivating example. So if we were interested in who grows faster, boys or girls, we might come up with a study. So this is just showing two individuals for simplicity, but basically we'd have a boys group and a girls group, and we'd take measurements at various ages. So here I'm just saying, like, let's just measure height at age 5, 10, and 15. And our two groups are the male group and the female group. So each individual is going to have multiple measures. If we only had two measures, like age 5 and 10, we might be able to get away with just doing the change in height. So height at age 10 minus height at age 5. And then you wouldn't have to use GEE. But as soon as we want to incorporate all three measures into basically how we're defining the outcome, at this point you need to use GEE, because at the individual level there's going to be, like for Jordan for instance, there's going to be correlation between his height at age 5, 10, and 15, and basically that's dependence in the data in these three measures. So GEE kind of expands on what you're able to do with something called one-way repeated measures, ANOVA. That's like the bivariate version. And the only thing you can't do with that is control for confounders. So you could only find like a crude relationship. But with GEE, you can have the variables that you're actually interested in, and anything that's confounding the relationship, you can control for that analytically and include it in the model. Okay, so going to the motivation of GEE, I've kind of already touched on it a bit too early. So basically, this green box represents what we're actually after. We want to find this group level effect of the change in growth rate, change in height rate, basically, between boys and girls. And we want to basically control for this individual level clustering. It's like it's a nuisance. It's not something that we're particularly interested in. We want to have it not affect the results, though. So basically the motivation of GEE is finding this effect of how the two green boxes compare without the effect of these blue boxes messing up that result. So this is an example of what it might look like, basically, just a mini GEE model where we have our outcome, height, we'd have the independent effect of sex, the independent effect of age, and the combined effect or interaction term between sex and age. So this link function, I guess, if it's not something you've heard, it's like how it's what puts everything else on an interpretable scale. So in logistic regression, the link function is like logit, And for linear regression, like what we'd probably be doing here, just because its height would be measured in centimeters, it would be like continuous. The link function's the identity function, so there would be no link function basically. So just kind of showing what these different variables are in relation to what we were talking about. So sex here, that coefficient would be basically the effect of sex on height, and that's represented here. The effective age we'd be able to find, and that's independent of sex because it's its own coefficient here in the model. And then what we're actually interested in, like the objective as written earlier, is what we're trying to find is kind of the effect of basically sex and age on height, where it's like you could replace age with time, because in a lot of analyses, basically it wouldn't be age necessarily, it'd be like time 1, time 2. And what we're doing with repeated measures is basically the interaction between this variable and time. So yeah, what this is permitting is for basically this relationship between getting older and getting taller. Does that vary by sex? Is that relationship different depending on if you're a boy or a girl? And what makes this different from a lot of other modeling is we also got to specify the correlation structure for these repeated measures. And basically there's a few you can choose from that I'm just going to go over quickly. And what I mean by that is we know that these, for Jordan and for Sarah, basically, like Jordan's different height measures are going to be dependent. Like if he was a tall 5-year-old, it's likely he's going to be a tall 10-year-old, like for example. And same with Sarah. So we'd have to kind of think about the correlation structure we're going to choose, and whatever statistical program you're using, you can basically just incorporate that into whatever, like if you're using SAS, like it would be one of the fields that you specify in the syntax. So exchangeable means that in this case we have 3 measures, and an exchangeable correlation structure would mean that every measure, each of these 3 repeated measures, is equally correlated to one another. So this first and second are correlated 0.8. That's just a random one I chose. Same with the second and third. And even the first and third are the same level of correlation, basically. And that's the simplest one. Autoregressive is a little more realistic, where measures that are taken closer in time are more likely to be correlated. So this first height and second height is 0.8, and this second height and third height is 0.8. Basically, they're fairly highly correlated, while the third and first are less correlated. Basically, they're taken farther apart in time. And something to note with this is, let's just say there was like 5 measures or more. Basically, every one that's one removed, like one measure removed, is always going to be 0.8. And anytime there's 2 removed, like if we had a third one here, that would also be 0.5. Like there's one for like that 1 measure removed, and there's a whole other one for 2 measures removed, and those are constant. And that's as opposed to unstructured, which is this last one I'm going to talk about, which is saying that basically every single measure relative to another can have its own level of correlation. So even though these are one removed, like 1 to 2 and 2 to 3 have a whole different level of correlation, basically. And basically, you don't need to come up with these numbers when you're fitting like this GEE regression. What you need to do basically is just specify which correlation structure you think it has. And from what I've read, it's pretty resistant to misspecifying the correlation structure. But basically, you're supposed to just specify what correlation structure you think it has, but you don't necessarily need to know these numbers. The program will come up with these numbers.